All right, so this one is about buoyancy and Archimedes principle. So the first thing we're going to do is we're going to go through a little derivation of where buoyancy comes from, and then we're going to do an example problem with this. So we've got an object here in water. It could be water, it could be any liquid, it could honestly be any fluid, it could be air. But we've got an object here. We'll say it's water because it's a little easier to think about it that way. This object is completely submerged at the moment. It doesn't necessarily have to be completely submerged, but again, it's easier to talk about it for the derivation if we imagine that it is completely submerged. Because of the fact that it's completely submerged, its two faces, its bottom and its top face, are going to feel forces from the different pressures on those faces. So we're going to have a pressure on the top face, which is P1, and a pressure on the bottom face, which is P2. And of course, force is equal to pressure times area. So then our forces are P1A and P2A. Force is pressure times area. All right, so let's see. As a result, now this difference in forces due to these pressures is actually what generates the buoyant force that a liquid exerts on something inside of it. That buoyant force is represented with that F sub B right there, B for buoyancy. And the size of that buoyant force is the difference between the forces on those two faces, the top and bottom face. So if we factor out the A there, we notice that we've got a difference in pressures. Now, we've been talking a bit about the different pressures in the depth of a fluid. The last couple of videos I did centered on that. And we've got this equation that relates pressure at bottom is equal to pressure at top plus rho GH. Let's rearrange that. And then we can plug in rho GH for this pressure difference, this P2 minus P1. All right, so that's what we've done right there. We've got that rho GH plugged in there. So we've got rho GH times A times area. Now, let's see. If I've got the area of maybe the top face of this cylinder, and then I've got the height of the cylinder, the volume of the cylinder is just going to be area times height. And so what are we let's plug volume in there for area times height. And what do we see? Well, now we've got our buoyant force is equal to rho times V times G. Well, what's rho? Rho's density. Density of what? Well, it's the density of, where did that density come from? Well, that density came from this equation right up there. And if we recall where that equation came from, that is the difference in pressures at various depths in a fluid. And that rho there is the density of the fluid. The H there is the height of the fluid. So when we get down here to the bottom in this buoyancy equation, that's telling us that the force of the buoyant force of a fluid is equal to the density of the fluid times the volume of the displaced fluid. So whatever the volume is of this object that's been submerged, whether it's fully submerged or partially submerged, whatever the volume is that's below the water is the volume of the displaced fluid. And that's what I would use there in that equation. So my buoyant force is equal to the density of the fluid times the displaced volume times G. All right. This is Archimedes principle. The equations that you see on, or the words that you see on the slide there are exactly what I described in words just a moment ago. So it says any fluid applies a buoyant force to an object that is partially or completely immersed in it. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. The weight of the fluid. So buoyant force is equal to rho of fluid times V, the volume of the fluid, times G. And then we recall that, well, density is equal to mass over volume. So then our mass would be equal to density times volume. We would end up with buoyant force is equal to the mass of the fluid times small g. And then as a result, those streaks on the screen really drive me nuts. And so as a result, my buoyant force is just equal to the weight of this displaced fluid. Usually the equation that we want to use for buoyant force is actually, rather than being the one that's on the slide itself, that's rather than it being this one. Typically the equation that I want to use is this guy right there, that buoyant force is equal to the density of the fluid times the volume of the fluid that's displaced times small g. All right, so let's take and do something with that. So we've got here a raft that's partially submerged. We're told that the top and bottom faces of the raft, it's effectively, I guess, a square, is 4 meters by 4 meters. So 4 meters by 4 meters. And that the raft, the thickness of the raft is 0.3 meters. Okay. Now, this thing is partially submerged, and our goal of this question is to figure out, well, what's the how much is it submerged? How deep into the water is it? And we'll just call that depth. We'll call it H. Okay. All right. So we know that we're going to use the buoyant force for this. We can see from our free body diagram right here that our buoyant force that the fluid's exerting on the raft has got to be the same size as the weight of the raft. If it weren't, then the raft would sink, and I guess sink all the way to the bottom. And if the buoyant force were larger than the weight of the raft, then the raft would rise up. And I guess I don't know. This doesn't make any sense. Float out of the water. But no, if the raft is staying at one level, then those forces have to be balanced. So my buoyant force is equal to the weight of the raft. All right. Let's do something first, though. Let's get some volumes here. The volume of the raft, is equal to, let's see, the area of the raft times we can call it height of raft. That's fine. This would be 4 meters times 4 meters times 0.3 meters. That would be the volume of my raft. Okay. Volume of water. This is the volume of the water that's been shoved to the side because of the fact that the raft is occupying its space. Well, it's still a 4 meter by 4 meter square. But now the height of that piece of volume would just be this H right here that we want to figure out what that is. Okay, so it'd be that H that we've identified as our unknown that we're interested in. Okay, there we go. So we've got those two expressions, those two equations for volume now, volume of raft and volume of water. One other thing that I'd like us to recall is that, let's see here, that mass is equal to density times volume. This means that if I'm concerned about the mass of my raft, then that's going to be equal to the density of the raft times the volume of the raft. Okay. All right, one other piece of information that we're given that I haven't highlighted yet. We're told that this raft is made out of pine wood, and that pine wood has a density of 550 kilograms per meter cubed. All right, so I've run out of space here. So what I'm going to do is I'm going to give us a blank page to work on. Okay, there we go. The forces have to be balanced. So my buoyant force has got to be equal to the weight of my raft. Okay, there we go. My buoyant force is equal to the density of water times the volume of water times G. And the mass of my raft is the volume of the raft times the, the density of the raft times the volume of the raft. Times G. Okay. So annoying. All right, let's see. Let's fill in what we have for volumes. Density of water times 4 times 4 times H times G. That's, remember in the previous slide, we said that the volume of the water was 4 meters by 4 meters, was 4 meters times 4 meters times H. Okay, and then on the right-hand side, we've got the density of our raft times the volume of the raft. This was 4 times 4 times 0.3. Okay, all right. Well, right away, we notice that we've got the same 4 times 4 on both sides. So, we've got effectively 16 on both sides. 16 and 16 is going to cancel. They're multipliers on both sides of the equation. The other thing that I notice is that I've got G on both sides of the equation as a multiplier. We can divide through by G and get that to cancel out as well. Okay. So what are we left with here? We're left with density of water times H is equal to the density of my raft times 0.3 meters. All right, if I rearrange this equation, divide both sides by density of water, I will get that density of water is, or excuse me, I will get to the height that my raft is submerged to is 0.3 meters times this ratio of my densities, density of raft over density of water. And I know what those numbers are. Let's see, 0.3 meters. The density of the raft, it's made out of pine wood, which has a density of 550. The density of water is 1,000. That's 550 kilograms per meter cubed and 1,000 kilograms per meter cubed. Because of the fact that the units are the same on the top of this fraction and bottom of the fraction, the units are just going to cancel out. That's why I didn't bother writing them in. And so as a result, our height, or rather our depth that this raft is submerged to is 0.165. That's so annoying. 0.165 meters. There we go. This also, incidentally, well, if we stare at this a little bit, we'll realize that 55% of the raft is submerged. It's the ratio of the densities there of our raft in the water. So 0.165 meters is our answer to this particular example problem. Right. So I've got one more thing here that maybe, okay, yeah, all right, okay. I've got one more thing here that maybe I want us to think about a little bit. So let's say that we've got a rectangular steel block and we've got some mercury available. Now, steel is less dense than mercury. Mercury is a liquid at room temperature and also well below room temperature. Well, we can actually float this steel block in mercury, place it down and it'll just float because it's less dense than the mercury is, which is kind of weird to think about steel floating, but there it is. So this steel raft will float in the mercury due to its lower density. Well, after we do this, we then carefully pour water into the container until the steel raft is completely submerged and there's extra water on top of it. So my question for you to think about for just a moment is what happens to the steel block as a result of adding the water? Does it sink lower into the mercury? Does it stay at the same level? Or does it rise higher in the mercury? So pause the video and think about it for a minute. Okay, it turns out, surprisingly, that it actually rises higher in the mercury. And this is kind of shocking at first until we really give it a little bit of thought. So now with the steel plug completely submerged, it's not only displacing the volume of the mercury that would like to be in its place. It's also partially, part of its bulk is submerged in this water. So not only does it have, part of it underneath the mercury, but it also has the rest of it underneath the water. So if we look, that part right there is submerged by water. This part right here is submerged in mercury. So that steel plug is effectively displacing two different fluids there. And so as a result, by adding the water in, we've really added another buoyant force. We've added a buoyant force due to water. So it's going to have two upwards buoyant forces, a buoyant force due to mercury and a buoyant force due to water. And as a result, it is going to rise up higher because it's got an additional force acting on it to balance out its weight. So kind of surprising, but there it is. And if you do a little YouTube video search of with some appropriate words there, you can absolutely find a demonstration of this. So kind of cool. All right.